There we go. Okay, right. We've started talking about ways that humans interact with the oceans, with all of this incredible diversity that we've seen of different life forms, different habitats, different environments, things that we get from the oceans, not just fish, but medicines and interesting chemical compounds. And today and Friday, I want to talk a little bit about the science behind global weirding. I've taken not to really like the term global warming, and the reason is that warm sounds positive. Global warming sounds like somebody is slowly turning up the thermostat and it's getting just a little bit more cozy. What I think we're in for, and a lot of this is pretty much baked into the system and is going to happen regardless of who we have as president or whatever. I think a lot of this can't be stopped now. What we're in for is increasing global uncertainty, less predictable, but certainly larger numbers of hurricanes, more frequent, less predictable episodes of flooding and drought and things like that. So a better word for, I think, what your lives are going to be like is global weirding. But let's see. Why do I say these things? Right. If you've had physics, you probably know this. In case you didn't, everything that is not at absolute zero temperature gives off electromagnetic radiant energy. Everything that's not at absolute zero is glowing. Sorry, let somebody in right here. And the hotter something is, the more energy it gives off. You right now are giving off radiant energy, electromagnetic energy. Sorry, I heard a ding dong, but don't see anybody I need to let in. And that energy is in the infrared spectrum, which your eyes can't detect. But if we put night vision goggles on you, you could. We could detect the radiant energy that you're giving off now. Naturally, if we were to heat you to a couple of 1,000 degrees, you'd start giving off visible electromagnetic radiant energy, meaning you'd be on fire. And if anybody's not clear, by electromagnetic radiant energy, I mean energy on the electromagnetic spectrum, which includes everything from radio waves to infrared to visible light to ultraviolet to X-rays and gamma rays. All of these types of energy that you can model as little waves with both an electrical and a magnetic field associated with them, traveling through a vacuum. So yeah, visible light being only one part of that. The hotter an object is, the more energy it gives off, and the shorter the wavelength of energy that it gives off. You're giving off long wavelength infrared. If I heated you to a couple of 1,000 degrees and set you on fire, you'd be giving off shorter wavelength visible light, even hotter. And the gas that used to be you might be giving off ultraviolet light. And if I really pushed it, it might start giving off X-rays. X-ray radiation is the kind of thing that, something as hot as an exploding star would give off a lot of. And anything that absorbs radiant energy also emits it. You're giving off infrared right now. If I was to sit you in the warm sun on a beach on a summer's day, I'd warm you up. As you warmed up, you would start giving off more infrared radiation. You'd absorb radiant energy and you would emit it. I used to do a lot of camping out in the desert out in the Mojave Desert, sometimes in summer. Probably not the smartest thing I've ever done, but hey, I was young and there were fossils to be found. And, all day, the rocks would soak up energy from the sun. And they just bake. There were days when you could hardly sit down. You'd feel like you were getting burned even through your jeans. There were days when you probably literally could fry an egg on the local rocks. I never tried it, but you probably could. And then at night, I'd bed down for the night in my sleeping bag, and some of my campsites would be hot at night because those rocks that have been absorbing all of that energy from the sun are emitting energy from the sun in the form of infrared radiation, which, by the way, is the same thing that keeps your French fries warm under a heat lamp. So basically, I would try to sleep in a ginormous heat lamp, and it was kind of unpleasant until the rocks finally cooled down. So objects absorb radiant energy, and they also give it off. And the spectrum that an object gives off is called black body radiation. A black body is not necessarily black. A black body is anything that absorbs all of the energy that falls on it and isn't undergoing any kind of chemical or nuclear reactions that are generating energy. Okay. Radiant energy, this electromagnetic energy, visible light, infrared, ultraviolet, etc., is the only way that energy can travel through a vacuum. Heat can travel by conduction. And if you want an example of that, get a piece of wire and hold one end between your bare fingertips and the other end in a flame, and you'll feel the effects of conduction pretty quickly. The heat will basically travel up that wire because metal's a good conductor of heat. Convection is heat that's transferred by movement of something that can flow. So we've talked about this way back when we started this course back in July, August of October 1976, or whenever it was. I'm completely losing track of time. But we talked about convection. That's heat energy that's transferred through flow. But the only way that energy can travel through a vacuum is by radiant energy on the electromagnetic spectrum. Light can travel through a vacuum just fine. So can X-rays, so can ultraviolet, etc. So virtually all the energy the Earth gets from the sun is through electromagnetic radiation. I'm assuming this is not completely new to you. Radiation can be absorbed like those rocks soaking up energy from the light of the sun. It can be transmitted like light passing through the lenses of my glasses, or it can be redirected. And redirection can either be reflection or scattering. Reflection you're familiar with. That's what happens when light hits a mirror. The light bounces off the mirror with the same intensity as before. The other possibility is scattering, where light bounces back in the form of weaker rays that are going in all directions. So if you look at, let's say, these kind of dull whitish walls of the classroom where I am right now, they're receiving light from the, what do you call them? Light bulbs, thank you, in the ceiling. And they are bouncing it off, but they're not bouncing it back in one common direction with the same intensity as before. If they were, they'd be mirrors. What they're doing is sending out that radiation in all directions in the form of a lot weaker rays And that means what my eyes see is not a mirror's reflection. They see a dull white surface. So that would be a case of scattering. So this happens when the sun shines on the Earth. About 30% of light energy that comes from the sun is reflected back into space. All of the planets reflect sunlight away from their surfaces. That's the way we can see them. Planets don't generate their own light. When you look up at the sky and you see Venus or Mars or Jupiter or the moon, what you're seeing is sunlight bouncing off the moon or those planets. You're not seeing their own light. So the Earth reflects about 30% of what hits us. About 20% is absorbed by clouds and atmosphere. So the clouds soak up radiation. So does the atmosphere. A case where the atmosphere does that you might be familiar with is the ozone layer up in the stratosphere. That's a layer of a type of oxygen, O3, or ozone, and that happens to soak up a lot, although not all, of the ultraviolet radiation that is traveling from the sun to the Earth. So that's a case of the atmosphere absorbing solar energy. And then about half of it is absorbed at the Earth's surface, like those rocks in the desert that absolutely got me baked, quite literally and not figuratively, when I used to camp out in the Mojave. Now, as we talked about, ozone efficiently absorbs about 97% of the medium frequency ultraviolet light in the lower stratosphere. And that layer does actually heat up. That layer of the atmosphere, about 12 to 19 miles above the surface, is hotter than the layers below it, because if anything absorbs radiation, it heats up. Now, longer wavelength ultraviolet does reach the surface, and that's the stuff that makes you tan or possibly dead from skin cancer if you get too much. But most radiation that the sun gives off goes right through the atmosphere. If the atmosphere absorbed all of that radiation, we wouldn't see anything because light wouldn't reach the surface. Okay, so the Earth's atmosphere doesn't absorb most radiation. The visible light from the sun goes right through and enables us to, see when we go outside. What the atmosphere is good at is absorbing long wavelength infrared radiation, and that is what the Earth gives off. The reason it was so hot in my old campsite in the Marble Mountains outside of Chambliss, California, in the Mojave, the reason why camping out there was not much fun in the summer was that those rocks were soaking up visible light, and they were getting hotter, and what they were giving off was long wavelength infrared radiation, just like just like you would get under a heat lamp. That's called re-radiation. The rocks, and to a lesser extent, the ocean, get warm because they're absorbing light and UV from the sun. And as they warm up, they start giving off radiation, and what they give off is infrared radiation. That's called re-radiation. And the gases, water vapor, good old H2O, carbon dioxide, CO2, and methane, CH4, happen to be very efficient at absorbing re-radiated energy from the Earth. So, sunlight travels right through the atmosphere. Sunlight is not absorbed by the atmosphere, so the atmosphere doesn't heat up because the sun is shining on it. But the atmosphere, the light that travels through the atmosphere hits the Earth, warms it, And the infrared radiation coming from the Earth warms up the atmosphere, in particular, certain gases in the atmosphere: carbon dioxide, water vapor, and methane. And as molecules of CO2, water vapor, and methane absorb energy from the Earth, they get hot. So the atmosphere warms up, and eventually those molecules radiate that warmth back to the Earth. The Earth is warmed directly by the sun shining on it, and it's kept warm by molecules of water, CO2, and methane in the atmosphere that absorb the Earth's radiation and re-radiate it back down. That's the greenhouse effect. That's technically not quite how actual greenhouses work. A slightly better example might be the Mylar thermal blanket effect, but we're kind of stuck with the term greenhouse for now. I don't know if anybody's ever done, very lightweight camping or anything like that, but you can get these blankets that are just sheets of very thin Mylar plastic made reflective on one side. And if you wrap yourself in one, they'll keep you warm despite looking extremely flimsy, because what they do is basically take your own body heat and reflect it back onto your own body. The atmosphere works in an analogous way. Here's the thing. I've been hearing in pop culture about the greenhouse effect at least since the early 90s, probably earlier than that. And it may seem like it's a bad thing, but if we didn't have it, the Earth's surface would get as cold as the moon's, right? The moon doesn't have an atmosphere. The moon doesn't have greenhouse gases that absorb radiant energy from the moon's surface and radiate it back to the moon. And the moon gets as cold as 153 below Celsius at night. Which reminds me of this bar I used to go to in my college years that was affectionately known as the Moon, because it had no atmosphere, you see. That was a joke. Anyway, there was actually a time about 750 million years ago in Earth history when we think, I'm just going to arm wave and say because reasons, the concentration of greenhouse gases in the Earth's atmosphere dropped unusually low, and we ended up with glaciers on Earth all the way to the equator. The Earth was frozen almost entirely solid for several million years. There were glacial deposits forming on every continent. I've seen a number of them. And exactly how life got through that time, I don't think we're entirely sure. But that was a time when we had fewer greenhouse gases, and it turned the Earth into something like the planet Hoth in Star Wars: The Empire Strikes Back, although without the Tauntauns and the Wampa ice creatures. By itself, the greenhouse effect is perfectly fine. If we didn't have greenhouse gases in the atmosphere, the Earth would be a complete ice ball. What the concern about is human-mediated release of greenhouse gases, especially carbon dioxide, that's driving a slow increase in average global temperature, aka global warming. If anybody's curious about this, or if anybody is likely to get into arguments about this with your drunk uncle at Thanksgiving dinner or anything like that, a few years ago, there was a debate about global climate change in, I think, the House of Representatives, and the rep from Oklahoma, James Inhofe, threw a snowball on the, or was it the Senate? Anyway, he threw a snowball and said that that disproved global climate change. Ha ha ha. Where he was screwing up was the difference between climate and weather. Weather is what you've got going on outside at any given moment. Climate is based on long-term averages of weather. The climate around here basically means we have warm and humid summers. August is especially miserable, and then it gets colder starting about in October. And we probably don't get snow on Christmas, but it might get down close to freezing. That's our climate pattern. Any given year is going to deviate from that just a little bit, but climate is basically the running average of what sort of weather conditions we get. Usually to calculate, average climates, you need at least 25 years worth of weather data. That's the difference between climate and weather. And for the record, all of this was worked out back in 1896 by a great Swedish chemist by the name of Svante Arrhenius. This is he. He's the guy who developed the concept of activation energy. If in your other classes you've had to study enzymes, right? That diagram where there's this hill that's keeping the ball from rolling down the slope and then the hill magically goes away. That was Arrhenius. So the basic physics of how this operates have been understood for over 120 years. This is not a particularly recent hoax. So global temperatures depend on concentrations of carbon dioxide in the atmosphere, and those are dynamic. They're constantly shifting. There are constantly things that are putting in carbon dioxide and also taking carbon dioxide out. And over the long term, these things tend to balance each other. So, for example, volcanoes put carbon dioxide into the atmosphere. Fire puts CO2 into the atmosphere. Whenever you burn something, when you burn something organic like wood, you turn that carbon into CO2 and you put it in the atmosphere. Decay puts CO2 in the atmosphere. The rotting of dead leaves puts CO2 into the atmosphere. And then other things will tend to scrub it out. Plants take CO2 out of the atmosphere so that they can turn it into more plant. CO2 can dissolve in water. CO2 can be taken up by living things in water and turned into shells. The carbon in the calcium carbonate of every seashell used to be in the atmosphere. Certain silicate rocks, as they weather, right, as they crumble and chemically break down in the atmosphere, soak up CO2. We say they scrub it out of the atmosphere. And with multiple sources of CO2 going in and coming out, eventually those tend to reach a balance. But comparatively little things can shift where that balance actually lies. Anytime a living organism dies, if it doesn't rot, if it ends up getting buried, that'll take CO2 out of the carbon cycle, possibly for many millions of years. The coal of Pennsylvania and West Virginia, and even the coal of Western Arkansas, although as of a few years ago, we only had one mine left. We used to have rather a large coal industry about 100 years ago around the towns of Clarksville and Scranton. All of that coal used to be mostly plants and trees growing in a kind of swampy environment about 300-ish million years ago. Those ancient trees lived and they died as living things do, and some of them rotted, but many of them got buried. And that took carbon dioxide out of the carbon cycle and locked it away for millions of years. Ultimately, the compressed plant material turned into coal. The same process happens for the production of petroleum, crude oil, and natural gas. Crude oil, by the way, mostly is made up of algae. People sometimes say the dinosaurs turned into oil, and I suppose that occasionally might have happened. But most petroleum is thought to come from buried and compressed plant material, and especially algal material, all those planktonic algae like dinoflagellates and things like that. Anyway, that locks carbon dioxide out of the cycle for millions of years. And then extracting and burning fossil fuels releases that ancient carbon back into the atmosphere. It puts it back in circulation. It would be like you finding a jar of coins from 1950 and not being interested in keeping them as a collection and deciding to spend them. You'd be taking money that's been out of circulation for 70 years and putting it back into circulation. And yes, they would all be legal tender. We've never had to, we have withdrawn certain coins from circulation, but we've never devalued them. So you could still spend a 1950 nickel if you wanted to, although it would probably be worth more to a collector than 25 cents. Anyway, never mind. So you're releasing that ancient carbon back into the atmosphere when you burn coal or oil. Here's Charles David Keeling, who set up a base on one of the two large volcanoes that make up the bulk of the big island of Hawaii, the mountain of Mauna Loa. If you follow this, Mauna Kea is the other one, and there's a large observatory up there, and controversy because it's also a sacred site for Hawaiian people, and they don't like having the telescopes up there. But anyway, Keeling set up a base on Mauna Loa and started measuring the concentration of carbon dioxide gas. It's very clean air. It's not downwind from any major pollution source. Global weather patterns mix the atmosphere very well. So this is a good place to sample if you want to see what the entire atmosphere is doing, or at least the entire northern hemisphere atmosphere. It does take a while for atmosphere in the northern hemisphere to mix with the south, but this is a pretty good place to measure what the average atmosphere is doing. And he found this. Think about this. The northern hemisphere, the northern part of it, is covered with enormous stretches of forest. That's the northern US, lots and lots of Canada, lots of Alaska, and certainly Scandinavia, and especially Siberia. All of that taiga forest in what's now Russia, all of it covered with forest. In spring and summer, the weather warms and those forests begin growing and they start putting out leaves. And to do that, right, they have to do photosynthesis, which means that they have to start taking carbon dioxide out of the atmosphere and converting it into biomolecules that the plant can use to make more cells, make more tissues, make more plant. And that's enough that it actually sucks down the global concentration of CO2. You can see that graph beginning in about May. Global carbon dioxide concentration starts dropping by as much as about 6 micromoles of CO2 per mole of dry air. That may not seem like much, but carbon dioxide only makes up about 0.03% of the atmosphere. There's very little, but even that little has a noticeable effect. Even that little has a strong effect because it's a greenhouse gas. So that growth of the northern hemisphere forest in the spring and summer sucks down CO2, and then when fall starts hitting, growth slows down of those northern forests. They stop putting out leaves. The leaves fall. The leaves end up on the ground, and the leaves decay. And the decay of those dead leaves returns most of that CO2 back to the atmosphere. So you can see the curve starts rising in October and keeps rising all the way to about May. And then once growth begins again, the cycle repeats itself, and the trees of the northern hemisphere forests start pulling CO2 back out. So it's kind of neat to think that this enormous biome of northern taiga forest actually has an effect you can measure all the way off in Hawaii. On top of that, however, there's on top of the annual cycle, there's been a longer term rise in carbon dioxide concentrations. We've gone from when he started, we've gone from about 310 micromoles of CO2 per mole of dry air up to about 410. So if you think about it, we have increased our global concentration of CO2 by about 25%. That raises average global temperatures. It doesn't take an awful lot of CO2 to have a noticeable effect, right? CO2 is only 0.03% of the total atmosphere. And yet 750 million years ago, when most of it got taken out, we had glaciers all the way to the equator. It's got a strong effect out of proportion to the raw amount that's there. The more that's there, the more efficient the atmosphere becomes at trapping heat. And the overall effect has been a rise in average global temperatures. And incidentally, the Presidential Scientific Advisory Board warned President Lyndon B. Johnson of the consequences of increasing global temperatures back in 1965. So basically, this is not news. We've known about this for the past 55 years. Even that doesn't show the whole picture. About 30 to 40% of that increase in CO2 is able to dissolve in the oceans, in lakes, and in rivers. And some of it can be, remember we talked about thermohaline circulation. Remember that cold water has greater solubility of gases. So not just oxygen, but CO2 can dissolve in that thermohaline circulation and go down into the deep ocean for hundreds of years. So we call that the solubility pump. CO2 is pumped down into the deep ocean by thermohaline circulation. And a second pump is the biological pump, because some of that increase in CO2 is taken up by photosynthetic organisms in the ocean, by algae, by seaweeds, by dinatoms and dinoflagellates and all that. Many of those get eaten, of course, but dead organisms that don't get eaten may end up buried in sediment for millions of years. You'll end up sinking to the bottom in the form of marine snow, and whatever doesn't get scavenged by hungry sea cucumbers or whatever it is may end up getting buried permanently. Given a lot of time, it may eventually form crude oil, but that's that's a matter for many thousands of years or more. And then some carbon dioxide gets taken up by algae and by animals to build shells out of calcium carbonate. And those two, if they don't dissolve, they may lock up that calcium carbonate indefinitely. I've got, here we go. I've got a little fossil shell right here that I'm holding up. It's the valve of an oyster called Exogyra, and it last lived about 70 million years ago, and it's made of calcium carbonate. So this little shell represents carbon dioxide that was in circulation back when the dinosaurs ruled the earth, got taken up by this oyster, and then the shell got buried somewhere outside of Arkadelphia, if memory serves, and got buried for 70 million years. If I wanted to turn it back into carbon dioxide, I could just drop this into some acid and it would fizz and dissolve, and the CO2 would go right back into the atmosphere from where it's been locked away for 70 odd million years. So dead organisms, dead organic matter, and shells can lock CO2 out of the cycle for millions of years, and we call that the biological carbon dioxide pump. The problem is that when the ocean gets warm, that actually works against both pumps. Remember, the solubility of a gas in water is temperature dependent. Cold water gas is more soluble than warm water. So if the oceans begin to warm, the oceans become less efficient at absorbing carbon dioxide. So the warmer the climate gets, the less the oceans can compensate for the warming climate by absorbing CO2. More CO2 also means that the oceans get more acidic because when you dissolve CO2 in water, you get carbonic acid, H2CO3. And so there's the estimated change in pH in surface ocean waters between the 1700s and 1990. And you can see that we estimate that it's all gotten a bit more acidic. Those green areas may be as little as 0.04 degrees pH. Within the brighter orange and red areas, it may be as much as 0.1 pH unit. That does not seem like much, but we're already starting to see effects. These are shells of, I mentioned these in a previous lecture briefly, and you may not recall, but one important component of ocean plankton is tiny snails modified for swimming with these little flaps. They're called pteropods. Some pteropods don't have any shells. Others have very delicate little shells. And even though each one of these is small, these live in huge numbers. When they die, the shells sink to the bottom, and there's parts of the ocean that are covered maybe several feet deep in what's called pteropod ooze. Just shell after shell after dead shell, each one of them may be the size of a sand grain. And we've already seen that if you raise pteropods in even slightly more acid ocean water, they have a much harder time building up their shells. It costs them more energy to make shells because the acid is constantly trying to take them away, and they can end up with pretty severely disrupted shell growth. So the warmer the ocean gets, the more acid it gets. Well, the more CO2 the ocean absorbs, the more acid it gets. The more acid it gets, the harder it becomes for critters like pteropods and forams and things like that to take CO2 out and put it into their shells. So the more CO2 is released, the less effective those pumps are at getting CO2 out of there. We're starting to see some economic effects from this itself. Beginning in 2006, we started seeing die-offs of oyster larvae. Up there at the left, that's what a normal oyster looks like on day one. That's the embryonic shell. And they have to develop shells rapidly within the first few days of life, or they're not going to make it. Lowering the pH even a little bit is enough to mess with shell building. On the right, you can see a shell of an oyster larva that was grown at a lower pH, and that can be enough to kill off the oyster. Given that oyster fisheries are economically significant in many areas, Louisiana, Florida, Chesapeake Bay, Maryland, Tomales Bay, California, and Oregon and Washington and other parts of the world, this is a matter of some economic concern. It doesn't take much of a pH lowering to start messing with the shell building and cause losses in your oyster larvae. And maybe this is not something you're accustomed to being concerned about, but this is potentially serious business for communities that depend on this. All right, I will stop the gloom and doom for right now, and we will pick this up on Friday. And I will stop recording now.